My name is Tsuneyoshi Sugimoto, and I'm a professor of the Graduate School of Engineering at Toin University Yokohama in Japan. Speaking of the new coronavirus, it is said to spread by splashing or contact. In short, it is important to keep a distance and not to touch. My research has no direct relationship with this new coronavirus, but I've been studying a non-contact acoustic inspection method that can detect defects from a long distance in a non-contact manner. So this time, I'd like to introduce the non-contact acoustic inspection method applied on part that can detect a defect using sound waves without touching the object from a distance. Using this method, I think it will be possible to inspect the outer walls of high-rise buildings and other high places which were difficult in the past. Background: accidents caused by degradation of aged infrastructures and falling of outer wall tiles from tall buildings are increasing. Non-destructive inspections for concrete structures are necessary because it is dangerous if the fall accident of a concrete or tile fragment occurs. Therefore, regular inspections are conducted. Visual inspection and hammering tests are still mainly used inspection method. Problems of conventional method as non-destructive inspection. The impact acoustics, ultrasonic, and electromagnetic methods have already been developed. However, these methods need to be used in contact with or close to contact with the object. Therefore, there is a problem that temporary scaffolding and aerial work vehicles are needed in places that are out of reach. Infrared and laser remote sensing methods have been developed as methods that enable non-destructive inspection from a distance of 5 meters or more. The infrared method can measure the temperature distribution without contact. However, it is not suitable for the inspection of the place where the temperature change is small, for example, inside a tunnel or under a bridge. The laser remote sensing method has a safety problem and requires a large amount of power. Furthermore, since the inspection points are slightly destroyed, the aesthetics of buildings are also impaired. Therefore, as an alternative method to the hammering test, we propose the non-contact acoustic inspection (NCI) method that enables safe and non-destructive inspection from a long distance. In this method, sound waves are emitted from a sound source and vibration energy is applied to the measurement surface. The distribution of vibration velocity of the target surface is measured by SLDV or LDV. Defects are detected by the flexural resonance vibration. So, NCI method is a non-destructive inspection method with high energy efficiency, measurable throughout the day with a small dynamo, utilizing flexural resonance, same as hammering test. From the results of verification experiment, it has already been clarified the NCI method can be applied in various places. For example, railway tunnels with curved shape, high bridge or viaducts over 30-meter distance, and short bridge with uneven surface. That sounds good enough, but of course there are problems. For example, if the distance is long, a big sound source is necessary. In the case of long distance, environmental noise increases. The upper part of the outer wall is difficult to vibrate because the sound source is angled with respect to the target surface. However, in the case of performing acoustic irradiation-induced vibration from an unmanned aerial vehicle (UAV), more commonly called a drone, these problems of the conventional NCI method as described above are solved at once. Considering about the advantages of the NCI method using acoustic irradiation-induced vibration from UAV, a compact sound source can be used since the distance between the sound source and the object can be shortened. Environmental noise problem naturally resolves because it becomes acoustic irradiation from short distance. Improvement in SN ratio and measurement speed is expected, since the influence of reflected waves on the laser head also disappears. In Japan, it is necessary to inspect the whole surface of all buildings constructed over 10 years before by the hammering test. But it is not realistic because of the large cost burden of temporary scaffolding, etc. Therefore, development of a non-contact type inspection method is required. The NCI method using acoustic irradiation induced vibration from UAV is likely to be a very effective method for outer wall inspection of tall buildings. Therefore, sun source mounted type UAV was actually manufactured. The base model is DJI Matrix 600 Pro, a flash speaker, a laser pointer, and a laser rangefinder, etc. are equipped in the lower part of this UAV. And this UAV weighs about 10 kilograms, and the available flight time is about 20 minutes. About drone controllability, the operation is relatively easy, and even a beginner like me can fly like a radio-controlled model. However, when approaching the wall like this time, be careful not to collide. Next, an outer wall tile specimen was also prepared for evaluation. The defects were simulated by placing strain sheet 0.5 mm thick and formed sheet 0.5 mm thick under the outer wall tile. The barrier depth is about 9 mm from the tile surface. In the first experiment, sun source was placed in front of the defect part. This figure shows the experimental result using vibration energy ratio. As shown in this figure, all defects can be detected. Since the flexion resonance frequency of 15 mm square was about 10 kHz, it was excluded from next measurement to shorten the measurement time. Next, sun source was placed in front of the central part of the outer wall specimen. This is to verify whether defects can be detected within the directivity range of the sun source even if the UAV swings by natural wind. Therefore, the directivity of the flash speaker used for UAV was measured. This is a measurement result of sound pressure distribution when the distance from the sun source to the concrete specimen is 4 meters. From this figure, it can be seen that if the tile size is about 2 meters, it is within the range of the sun source directivity. Therefore, as shown in this photograph, an experiment was conducted in which the sun source was placed to the central part of the outer wall specimen. At this time, the UAV itself is fixed on the table and measured from a distance of about 3 meters. Experimental result example using vibration energy ratio is like this. Since in indoor experiment, it contains some noise due to the influence of multiple reflections. But important thing, even if the sun source does not face a defect, it was confirmed that the wide range can be scanned as long as it is within the directivity range. Next, we conducted a acoustic irradiation experiment from UAV in flight. Outer wall specimen was lifted on the other concrete test piece by crane to simulate the actual outer wall. SADV is placed below the front of the outer wall specimen, and UAV is about 3 to 5 meters away from the center of the front. Flight altitude is about 4 meters. This is a video of the experiment. From this position, due to the directivity of the sound source, the emitted sound waves are hardly heard, and it can be seen that the UAV's propeller sound is louder. Next, a clear reflected sound can be confirmed at a position directly behind. I'm trying to irradiate acoustic waves to the center of the specimen, but the UAV itself is shaking due to the influence of natural wind. This is an example of the measurement result by the vibration energy ratio. From this figure, it can be seen that the large defect can be detected, even if the UAV swings by natural wind. How about other small defects? Other defects can also be detected by applying signal processing that takes into account the sound source position. This research was carried out with the following grant or assistance. We'd like to express our sincere gratitude to all those concerned for their cooperation. Thank you for your viewing.